Let's now look at sample problem 23.1.2. If you have not watched the video on the previous sample problem, please do that first, because this sample problem is very similar to the previous one. In this sample problem, we have a Gaussian surface that looks like a cube. And this Gaussian surface is sitting in an electric field given by a vector that has both an x and y component. And the problem is wanting us to calculate the electric flux through the right face of the cube, the left face, and the top face. Let's first look at the Gaussian surface. And once again, we want to recall that little funny diagram that we used earlier. And this diagram tells us that for each surface element that we're going to look at, we want to look for two vectors, the electric field E and the surface element dA. For the current problem, where the Gaussian surface is a cube, and for the first part, where we are supposed to calculate the electric flux through the right face. So here I have added some shades to the right face, and on that right face, we need to look for the electric field E and the surface element dA. And once again, since the Gaussian surface is a closed surface, the direction of a surface element should be pointing outward. And in this case, that outward direction will be horizontal to the right. So we can write the vector dA in its component form like this. And the electric field is given in that expression. Between the two, we can form a dot product, and that will be the electrical flux for this surface. And we can apply the formula for the dot product to obtain the result. Notice that the unit vector I and the unit vector j are perpendicular to each other, and therefore the dot product between them will become 0. Just like before, we are now going to apply basic calculus to obtain the result of the integral. Now, here you have to realize that in that integral on the right hand side, that x in integrand is not a variable. It is actually a constant. To see that, we'll have to again look at this little funny diagram. It does not matter which surface area that you are looking at. You have to look at the electric field in that surface and the corresponding surface element vector dA. In other words, the electric field has to be the vector located on that surface. Now if you look at the Gaussian surface again, and on that right face, the electric field E has the same x component over the whole right face, which means that that x is actually a constant. We can point at different locations on that right face. At any of those locations, the x is the same. And by the way, that x has a value of 3 across the whole right face. Therefore, we need to treat x as a constant and move it to the front as we did before. And once again, we can apply basic calculus to complete the integral. Now, we'll use a lower script r to represent that this is the electric flux for the right face. And like I said, on this right face, the x has a value of 3.0. So let's plug that in. And we'll also need the value for the area of the right face. Now if you look at the diagram, it looks like the side of the cube is 2 meters. And therefore the area of the right face should be 2 squared, or 4. Altogether, and we'll have a value of 36. And from the definition of the electric flux, we can calculate the unit for the electric flux. The unit for the electric field is Newton per Coulomb. The unit for area is meter squared. Therefore, the SI unit for electric flux is Newton meter squared on top and Coulomb at the bottom. Let's now do the calculation for the left face. From the diagram that we have, we can't see the left face, but it is just the face that's on the opposite side of the right face. And because the direction of the surface should be pointing outward, therefore, for the left face, the direction of the surface should be pointing to the left or in the negative x direction. And we can write down expression for the dA in its component form in the following way. Any electric flux on the left face will be obtained in the same way. Notice that the y component of the electric field has no contribution here. because the unit vectors I and j are perpendicular to each other, and the result of the dot product between them will be 0. From here, we'll repeat the integration just like before. And just like before, that x in the integral is actually a constant because the x component of the electric field does not change over the left face. And here we want to know that x has a value of 1.0 on the left face. And we can see this from the diagram. So we will plug 1 into x. Let's now repeat the calculation for the top face. And here I have added some shades to the top face. And once again, you want to see that since we have a closed Gaussian surface, for the top face, the direction of the surface is pointing outward or in the right direction. So for the top face, the surface element can be written in its component form this way. Any electric flux can be obtained just like before. Now notice that this time it is the first term that will become 0. But it will be for the same reason, because if you look at that first term, that is a dot product between unit vector I and unit vector j. And we will do the integral just like before, but this time we do not have a variable to worry about. So that's how you calculate the electric flux when the electric field is not a constant. I would say that the most difficult part of this problem is to see that x in the integral is actually a constant. And that completes this video.